Hi, my name's Stuart Lindsay, and I brought biophysics to ASU back in 1979, and I'm proud to say that it's now, I believe, the largest single biophysics group in the country. I got into not just biophysics, but nanoscience in the early 1980s with the invention of the scanning tunneling microscope, and my group currently does a lot in scanning probe microscopy. But the main focus is bio-nanotechnology, which I both practice in research and teaching. And my book, cover of which you see here, is used in many introductory nanoscience classes around the country. If you want to get a hold of me, my email is my name, stuart.lindsay@asu.edu. And you can find my website by going to Google and searching on the Biodesign Institute and looking for single molecule biophysics. So I have great collaborations with a large number of just incredible colleagues in the Center for Biological Physics, but I'm going to focus in on just one project in my group to show you what we're doing. So the current focus is single molecule bioelectronics. And in this, we do several things. We design custom protein molecules to carry out certain electronic functions and use the scanning tunneling microscope to make measurements on those devices. To translate this work into commercialization, we need chips so that we can make these devices at scale. So we have a very large effort in making bioelectronic chips that incorporate enzymes, for example. Of course, as a physics department, we want to understand what we're doing, and probably, I hope to many of you, it comes as a surprise that proteins conduct at all, let alone conduct very well and convey useful information. And of course, we want to understand how this can be. And so we have a large program of measurements in my lab and collaborate with theorists both here in the Center for Biological Physics and elsewhere to develop quantitative models of what we measure. And we are zeroing in on an understanding of electronic conduction in proteins. Finally, we want to use this knowledge as one very specific project to build devices that can sequence single molecules of DNA or single protein molecules. And to illustrate how this, we hope, will work, I'll show you the example of a single molecule DNA sequencer. So we take a pair of electrodes, we functionalize them with small molecules called biotin, which strongly bind proteins called streptavidin. The streptavidins will bind 4 biotins, so there are 3 sites left for binding something else. And so we then engineer a polymerase, which is the enzyme that copies DNA, with 2 biotins on it so that it can bind and bridge the gap. So now we can measure the current through this molecule, and as the molecule fluctuates, so does the current. So let me just show you one example of a current versus time recording taken as one of the essential ingredients to copy DNA. The nucleotide triphosphates are added to the mix after the polymerase has bound a template to be copied. So here we go. Here is the current prior to adding the nucleotide triphosphates. We then add them, and what we will see is that as the polymerase closes to start its action, the current jumps up really dramatically. There it goes. And in the high current state, you'll see lots of fluctuations. Those fluctuations reflect the incorporation of successive nucleotides in the extending DNA molecule. And by understanding the information in those signals, we hope to be able to sequence single DNA molecules and eventually extend this technology to sequencing single protein molecules.